Thank you, Dr. Niranga. So it's my pleasure and privilege to introduce the first speaker of this symposium, eminent Professor Hema Karunadasa. Hemamala Indivari Karunadasa is an associate professor of chemistry and senior fellow at the Precourt Institute of Energy at Stanford University. She works on hybrid organic-inorganic materials such as perovskites for clean energy and large area lighting. Hema grew up in Colombo, Sri Lanka. She was a student at Ladies College, Colombo. She wanted to be a medical doctor, but the time gap between high school and university led her to apply to universities in the United States. Although she was not too serious about it at the time, when she got the admission from Princeton University, there was no hesitation in accepting that offer. At Princeton, Hema worked with Professor Robert Cava on the geometric magnetic frustration of metal oxides. In 2003, she graduated with a degree in chemistry and a certificate in material science and engineering from Princeton. It was Professor Cava who inspired Hema towards an academic career. The excitement for inorganic chemistry started at Princeton, paved the way to her doctorate from the prestigious University of California, Berkeley. There she worked with Professor Jeff Long on heavy atom building units for magnetic materials and electrocatalysis for water splitting. Probably the most exciting research experience of her academic career took place while she was in the Long group as a graduate student, when she discovered a novel material just before she threw away the washings of the remains of her reaction vessel. After obtaining her PhD from UC Berkeley in 2009, Hema continued to study molecular electrocatalysis for water splitting during her postdoctoral research with Professors Jeff Long and Christopher Chang. She further explored molecular catalysts for hydrocarbon oxidation as a postdoc at the California Institute of Technology with Professor Harry Gray in 2011. Hema's independent academic career started in 2012 as she joined the faculty at the Stanford University. Hema received numerous honors and awards. In 2020, she was awarded the Harry Gray Award for Creative Work in Inorganic Chemistry by a Young Investigator, which was awarded by the American Chemical Society. Among other honors are the Terman Faculty Fellowship, NSF Career Award, ICCC 41 Rising Star Award in 2014 at the 41st International Conference on Coordination Chemistry, and many more. She currently serves as the editorial advisory board member of the journals Chemistry of Materials and Inorganic Chemistry, and this year she also took the role of associate editor for Chemical Science. She is a shining star in the world of materials chemistry research with an H index of 42, over 100 research publications, several patents, and over 10,000 citations. Professor Karunadasa, I am sure that the young scientists who are participating in today's symposium will be inspired by your passion for research. I would now like to invite you to enlighten us on the topic, teaching double perovskites to absorb sunlight. Please note that the Q&A session after this talk will be moderated by my colleague, Dr. Hasini Pereira. Professor Karunadasa, over to you.
Thank you very much, Ashani, for that very detailed introduction. Well, it's really a great honor to be able to join you for the centenary celebrations for the Faculty of Science at the University of Colombo. As Ashani mentioned, I grew up in Sri Lanka, in Colombo. In fact, I lived really close to the University of Colombo. And I never got a chance to visit the university. I wasn't qualified. But I do remember playing hockey in the university grounds because my school, Ladies College, was just very close, and we would have hockey tournaments at the University of Colombo. So I'm not sure what I can do with a hockey stick these days. Unfortunately, I think my chemistry skills have risen at the cost of my hockey skills. So today I'll talk to you about chemistry. Niranga asked me to talk to you about perovskite solar cell absorbers. So I'm happy to do that. Most you may have already heard of perovskite solar absorbers. Most talks that you may have heard will probably talk about their incredible properties. And that's because these materials do have some really remarkable semiconductor properties. And features as solar absorbers. But I'm going to give a slightly different talk. I'm going to talk about all of its problems. And I'm going to try and persuade you that chemistry has lots of tools that will help us solve these problems in the future. So I will share my screen. Okay, so the title of my talk is on how to teach halide double perovskites, how to absorb sunlight. And first, let me introduce the family of materials that I love so much, the family of perovskites. Perovskite just means a crystal structure. It just describes an arrangement of atoms in a solid. So if you were to look very closely at a solid that adopts the perovskite structure, you will find a metal that is coordinated by 6 ligands. If you are looking at a halide perovskite crystal, these ligands will be halides. So you will find a fluoride, a chloride, a bromide, or an iodide. And these metal halide octahedra connect to other octahedra through shared corners. And this describes the perovskite structure. This turquoise framework that I show you here has a negative charge. So to balance that charge, we find positive ions residing in the cavities. When this positive ion or cation is an inorganic ion like cesium, potassium, rubidium, this would be your standard inorganic halide perovskite. But you can also imagine stuffing small organic cations into these cavities as well. For example, methylammonium will fit this cavity. And in that case, these materials are called organic, inorganic perovskites or hybrid perovskites. If I were to try and stuff in an organic molecule that's slightly too large for this cavity, we can still form a perovskite, but often we'll find a lower dimensional analog, like this 2-dimensional perovskites shown here. So my favorite aspect of these materials is how they form. So when I was an undergraduate, I worked with oxide perovskites, which are forged in a furnace at 1500 degrees over the course of a few days. In contrast, the halide perovskites form in a pot of water at room temperature. So these materials form through a process called self-assembly, which simply means that the ions in solution do what they want to do. So if I were to take a pot of water and throw the organic and inorganic precursors to a perovskite, you can imagine in solution, there's this crazy mess. And our job is to try and persuade this big mess to form these beautiful ordered structures. And they have to form it of their own accord. So we don't force them. I like to say we persuade them by changing the crystallization conditions. The beauty of self-assembly is that, well, let me start with the challenge. The challenge of self-assembly is that 100 different structures can form. So how do we get these ions to form the particular structure we want? The beauty of self-assembly is that once those conditions are identified, you can make the same structure every single time. You can scale it up, you can make grams of this stuff, you can take a solution, you can deposit a film of this material on any substrate, which is really important for making devices. Everything is cheap and scalable and reproducible. So the material that has really caught the photovoltaic industry by storm is shown here. This is the perovskite that I initially introduced. There's lead in the center and iodides surrounding the lead. These lead iodide octahedra share corners to occupy 3-dimensional space. And in these in these voids, we find methylammonium as the A side cation. This material is not new. It's been known for decades. But in 2009, Miyasaka's group decided to evaluate this material as a photosensitizer in a solar cell, and they got a really decent device efficiency of 4%. And the great excitement in this field is at how quickly these device efficiencies have risen. Just to put this in perspective, so 20% is commercially viable. So to put this in perspective, any other material that has been evaluated as a solar absorber has taken 50 years to reach a commercial viability. And this little trooper just skyrocketed. So this is great. I will point out that when you see this rapidly climbing graph, you say to yourself, something's got to be changing. It turns out that what was changing was not the material itself, but various aspects of device engineering. Scientists figured out how to make better films, better layers of your photovoltaic device. The perovskite absorber that's used is still more or less the same material. So this raises the question, is this material, the very first material to be evaluated as a solar absorber, is this the best? Or does it have problems that we cannot address through engineering? We cannot just put a layer on top of it. Are there problems that are inherent to the composition, inherent to the structure, that we can really only address by making a new and improved material? So the strengths of this material are many, but I will only talk about its problems. In the spirit of criticizing most those you love, I will look very critically at these materials, and today I will point out just two of its problems, but I think two of its biggest problems. So the first is that we noticed very quickly, along with anyone else who has worked with this material, that it's not stable to moisture. So the black solid, methylammonium lead iodide, will decompose under ambient conditions and form yellow lead iodide, probably faster in Colombo than in Palo Alto. And once you get yellow lead iodide, you basically don't have a solar absorber anymore. So this means that that if you're trying to make perovskite devices in large scale, all of your manipulations have to be done under strictly water-free conditions, which is quite hard to do, which will really increase manufacture cost. And of course, the material will have to be rigorously encapsulated as well. So we wanted to engineer moisture resistance into the material, not as a layer you deposit on top of the material, but as something that's inherent to the material. So my group showed the first example of a two-dimensional perovskite solar cell, where we found that if you were to form a 2D perovskite with thick inorganic layers, these thick layers that look like we have cut ourselves a very generous slice of my 3D perovskite, these inorganic layers can absorb sunlight and generate current, just like a 3-dimensional perovskite. But now we have this additional layer, this organic layer, that repels moisture. So it's almost like we have taken a 3D perovskite, sliced it, and coated it with something that repels moisture. So these materials are much more moisture stable. We can form perovskite solar cells just out under ambient conditions. And in our first report, we had a device efficiency of, I forget, something like 4-point-something%. But since then, the device efficiencies of 2D perovskites have also rapidly risen as more and more groups around the world have been looking at 2D perovskite solar absorbers. So we ended this first report by saying that as you increase n, which is the number of layers in the inorganic layers, so this is n equals 3, we predicted that as n gets larger and larger, even if you have a single phase material or even if you have a mixture, you will get higher and higher device efficiency as n increases, while the organic layers can still provide moisture resistance. And this is exactly how the field has progressed. And efficiencies of 2D perovskite solar cells are now rising. It's important to remember that in these films, especially with high n values, we are almost always faced with a distribution, which is kind of interesting to think about. So the large n values basically act like your 3D perovskite, absorb sunlight, generate current, and the small n values bring with it more organic groups and repels moisture. So we were fairly pleased with this result that you can now form perovskite devices out in air, but it wasn't entirely satisfactory because we knew that both 2D perovskites and 3D perovskites contain a water-soluble source of lead. So these materials are toxic sources of lead, and the toxicity effects are compounded by its water solubility. So, we've spent the past few decades trying to remove lead from our households. It's less than ideal to coat our roofs with a water-soluble source of lead. I will point out that there'll be very little lead in a perovskite solar cell because you only need a very thin layer. However, we certainly have to think about getting rid of this lead, at least for the next generation of perovskite solar cells. So this is also a fundamentally interesting chemistry question. how do you get rid of lead without getting rid of its properties? So we want to make a functional analog. So here I want to take a step back and ask, what do you mean by an analog? So there are lots of perovskites already known that don't have lead, but they don't absorb sunlight. So we don't want a structural analog. We don't want something that looks like the lead perovskite. We want a functional analog, something that acts like the lead perovskites with respect to photovoltaic properties. So what do we want? Well, first, we want a semiconductor. We want a material with filled electronic states, a band gap, and empty electronic states. And this band gap has to be sort of moderate. The ideal band gap for a solar cell with one absorber is 1.4 eV. We're going to put this absorber in a solar cell. So this is an energy diagram for a solar cell. This is my absorber. So sunlight hits my absorber, promotes an electron from my filled bands to my empty bands. And then the electron has to move to the electron conductor, and the hole has to move to the hole conductor. And when the electron and the hole recombine, that's the current that I get out of my solar cell. And this energy difference here, that's the voltage I can get out of my solar cell. So I want a material that absorbs sunlight very strongly and very, very efficiently, promotes an electron from my filled bands to my empty bands. And then I don't want that electron to just pop right back down, then, because nothing happens then except I get light. Instead, I want the electron and the hole to hang around for long enough and diffuse through the material and find the current collector, the electron conductor and the hole conductor. So what do I want in my solar absorber? I want a material that absorbs sunlight very efficiently. And I want a material where those carriers, the electron and the hole that I mentioned, hangs around for long enough and is mobile enough that we can get current out of the electron and the hole. So why is the lead iodide perovskite so great? Because it has a direct band gap of 1.6, which is pretty close to 1.4. So a direct band gap material is shown here, and a direct band gap material absorbs sunlight very efficiently. Some materials have an indirect band gap, and those materials are less efficient at absorbing sunlight. So it absorbs sunlight very weakly, which is not a deal breaker. It just means that you need more of that material. So with a direct band gap material, you need a thin layer of an absorber. With an indirect band gap material like silicon, you need a thick layer of the material. And we also need long-lived electrons and holes, or carriers. The lead iodide perovskite, the carriers live for microseconds, which is really a very long time in the time scale of a photovoltaic device. So if someone posed this problem to me, and I knew nothing about photovoltaics, and I knew nothing about perovskites, and someone just told me, hey, what ion is going to act like lead 2+, I'm going to pull my periodic table out, as would many of you, and say, well, thallium 1+ has the same electronic configuration as lead 2+, as does bismuth 3+. So if you look at the band structure, a very simplified band diagram of the lead perovskites, you see that the valence band has lead s character, filled 6s electrons, orbitals, and the conduction band has empty 6p orbitals. So thallium 1 has the same electronic configuration as does bismuth 3. So thallium 1, or thallium in general, is more toxic than lead, 10 times more toxic than lead. Bismuth is non-toxic, right? Bismuth is even used in drugs. So as a first step, we decided to take bismuth 3+ and see whether we can incorporate it into a perovskite. Except that bismuth doesn't want to go into a perovskite. Bismuth is 3+, lead is 2+, and 3+ ions prefer different coordination environments and different connectivity. So it turns out that bismuth prefers low-dimensional structures. So we needed to be clever about persuading bismuth to go into a perovskite lattice. And we found that we could do this quite simply by working with another subfamily of perovskites known as double perovskites. So these materials have also been known since the 1800s, but we were amongst the first to evaluate these materials, evaluate double perovskites as solar absorbers. So in a double perovskite, instead of a single metal, we have two octahedral metals, B and B prime. They alternate in all three dimensions. And in a single perovskite, this octahedral metal site has to be 2+. In a double perovskite, the average has to be 2+, but we can distribute that charge unequally as 1+ and 3+, or 2+ and 2+, or nothing and 4+. It still averages out to 2+. Adam found that silver and bismuth goes into a double perovskite, and he was able to form this glorious crystals where the morphology of the crystal reflects the cubic symmetry of the lattice. And we decided to evaluate this material as a solar absorber. So first thing to note is it's red. It's not black as a solar absorber should be, so the band gap is probably too high. And indeed, the band gap is indirect. So that means it absorbs sunlight very weakly, and the band gap is too high for a single junction absorber. There are solar cells which could use this band gap. But the band gap is indirect, meaning that you need a thick layer of this material. So as I mentioned, silicon, which is in the commercial solar cells, do have indirect band gaps. But this is not a problem because you can simply use a thick layer of silicon. And the reason you can get away with a thick layer is because the photogenerated electrons and holes have a very long carrier lifetime, so that it can find its way out of this really thick layer and find the current collector. So the question for us is, what about the silver bismuth double perovskite? Does this material have long-lived carriers? So we did a whole bunch of spectroscopies. I'm not going to go into technical details in this talk, but feel free to ask me questions at the end. And we find that this material has really long-lived carriers that can diffuse very long distances. So this is really good news, and it tells us that if someone were to be able to make a micron's thick layer of a double perovskite, this material should be an efficient solar absorber. To date, no one has been able to make this thick layer. This is an ongoing challenge. So I think the best part of this research is that we really opened up the entire periodic table for our explorations, because previously we were stuck with a 2+ metal, and there simply were no good options for stable materials that we could look at. With double perovskites, we have many more options. In fact, you might argue that we have the opposite problem, that we have too many options. So now we can put a 1+, 2+, 3+, or 4+ metal into these octahedral sites, and the choices are frankly too many. How do we know which two metals to pick to get the band gap that we want? So we recently wrote a mini review on double perovskites, and we make this gambling analogy. So if you engaged in any kind of contest and you decide to double the stakes, that means instead of winning the first bet, you have to place 2 consecutive bets, and you have to win both in order to win, but your reward is greater if the stakes are doubled. And that's exactly how we feel about double perovskites. It's harder to pick 2 correct B-site metals compared to just 1, but we think that there will be many rewards to come if we really figure out how to pick these 2 B-site metals. So we want to be able to predict the band gap magnitude, the size of the band gap, as well as the band gap symmetry, whether we get a direct band gap or an indirect band gap, based on the two B sites that we pick. And we want to be able to predict this before we make the material, of course. So let me show you how much progress we've made in this respect. So first, we should always start with something familiar, so we can look back at the lead iodide perovskites. And here I'm showing you a simplified band diagram of this material, where I'm highlighting the metal orbital contributions. So the valence band has lead 6s character, the conduction band has lead p character. So the band gap transition is an electron going from an s orbital to a p orbital on the same lead. And at some level, these orbitals are fixed, right? It's the same atom. We can change the halide, and this halide changes mostly the valence band, and that allows us to tune the band gap to some level, which is useful. But with the double perovskite, we have a whole new handle to tune. And that's because the band gap transition is different. So here I'm showing you the band structure. I'm showing you the same band structure twice of the silver thallium double perovskite. because I want to show you the individual metal contributions. So I see that if I look at the valence band, it has mostly silver character. There's practically no thallium character. And if I look at the conduction band, it has mostly thallium character. In other words, if I look at the band gap transition, it is an electron moving from silver to thallium. It's a metal-to-metal charge transfer. So metal-to-metal charge transfers have been seen before in chemistry. This is one of my favorite examples. So you might have seen this famous Japanese print before. It is of great historical significance. Art historians will talk about, the serene Mount Fuji in the distance and the turmoil faced by these fishermen who are about to get crushed by this big wave. And I'm not an art historian, so I should probably stop there. But I can also point out that as a chemist, this print is of great significance because this is one of the first examples of this blue, this dark, deep, rich blue is one of the first synthetic blue pigments to be made. And this material, this dye is called Prussian Blue. It was synthesized by a pigment maker in the 1700s, and he was trying to make red paint. So he clearly messed up, and chemistry is full of such happy accidents. So he accidentally made this blue paint, and today we can look at this material much more closely using X-ray diffraction, and we know exactly where all the atoms are, and we find that this has a familiar arrangement of atoms. So we have iron octahedrally coordinated by cyanides, and these cyanides form this metal cyanide octahedra that share corners and extends in 3 dimensions. So this is what Prussian blue looks like, but why is it blue? Well, there's an ion 2 and an ion 3, and an electron hops from ion 2 to ion 3. It takes energy for this electron to hop, the same way it takes energy for you to hop. And it turns out that the energy required for this electron to hop corresponds to the energy of yellow light. So when sunlight hits Prussian blue, it absorbs yellow photons and the electron hops around. And this is the color wheel. You might have encountered this before. A material that absorbs yellow light will reflect its complementary color. So it reflects blue, and that's why it looks blue. So when a blue photon hits Prussian blue, it gets bounced back, it hits my eye, and my eye says, that's blue. So I told you the structure looks familiar, and I hope you all see lying in here a perovskite. If you were to change the cyanides to a halide, we find the perovskite lattice. So, historically, materials have been given different names, but it is very useful to draw connections based on their structures. So Prussian blue is a perovskite, just like El Paso light is a perovskite. And by making these connections, we can actually learn. We can apply the lessons that people have already learned from Prussian blue now to El Paso lights. So the same metal-to-metal charge transfer that dictated the color of these pigments might now teach us how to design El Paso lights that can absorb sunlight. So this is my very simplified band structure of the silver bismuth chloride double perovskite, where I'm simply trying to show you that the band gap transition is an electron moving from silver to bismuth. So I can extrapolate from this band structure to the molecular orbitals that form the bands. And I can say, well, this is the approximate energy of the silver hexachloride highest occupied molecular orbital. And this is the approximate energy of the bismuth hexachloride lowest unoccupied molecular orbital. And there are all kinds of spectroscopies available that allow us to actually figure out what are these energy levels of these molecules. And likewise, I can look at this thallium-1, thallium-3 double perovskite and extrapolate from the band structure to the bands. And this tells us that if we were to pick molecular orbitals, so this is the metal hexahalide, molecular orbitals that inherently were close together, we can then form double perovskites with unusually small band gaps. So the band gap of the silver thallium perovskite is much smaller than your standard double perovskite for 2 reasons. One is because we are starting with molecular orbitals that were already close together. And the second point is that s orbitals are, fluffy and dispersive, and they interact very strongly with each other, and therefore any band formed by s orbitals is more dispersive. So, chloride perovskites are usually colorless or yellow. They don't have any business being black, except when you correctly pick the B sites. So we can go from the band structure to the molecular orbitals. And this helps us predict which two B sites can give us a small band gap. But we should surely be able to go the other way as well. We should be able to go from the molecular orbitals to the band structure. And there's, I hope I can persuade you that there's value in this as well. So my students decided to do this using their knowledge of group theory. So if you are a chemistry undergraduate, you probably have encountered group theory, or if you haven't, you probably will. And if you're thinking of going to graduate school in chemistry, you're going to learn it again. So if you're anything like me, you will learn this and you will immediately forget it. But the beauty of learning something is that even if you forget it, you can easily teach yourself anything that you need to know if you ever need to use it again. And so that's basically our story as well. So all three of us retaught ourselves group theory and decided to use just a pencil and paper to come up with the band structure of double perovskites to see how much information we will get from this process. So Niranga told me that there might even be high school students in the audience. So if you haven't encountered group theory, just don't worry about the next two slides, and I'll catch up with you. If you have encountered group theory, you know that you start with the halide atomic orbitals. You use the point symmetry of the metal, that's an octahedron, and you can construct your symmetry-adapted linear combinations of ligand orbitals. And these are the salks. So this up to here is, I think, very standard in the chemistry curriculum. You may not have encountered the block function, which you use for solid state structures. So basically you use translation as another one of your symmetry operations, just like reflection or rotation. So with the block theorem, you take your halide salk and you propagate this in three-dimensional space using the symmetry of the double perovskite. And this gives us halide-only wave functions. And at this point, we add the metal frontier orbitals and we evaluate bonding, non-bonding, anti-bonding interactions. So the beauty of this method is, well, first of all, we're only using a pencil and paper. We are not using any computers. And the beauty is that we are not adding metals until the very end, meaning that this method is generalizable for all double perovskites, not for a particular metal combination. So in pictures again, I start with molecular orbital theory and I construct my halide-only octahedron. I then use block theorem to propagate this in three-dimensional space. And then I add my metal orbitals and I evaluate bonding interactions with the assumption that any band extrema has to be where bonding or anti-bonding interactions are maximized. And using, so this this is a theorem which sounds complicated, but every step that you apply is pretty simple. And by doing this, we are now in a position to be able to predict, if we were simply given a composition and we were told these are your two B sites, we are able to predict with a fairly high degree of accuracy whether the material will have a direct band gap or an indirect band gap. So all we need to know are the frontier orbitals of the two B sites. And that tells us the valence band maximum and the conduction band minimum. So now we can predict the size of the band gap based on the energies of the molecular orbitals, and we can also predict the direct versus indirect nature of the band gap simply by looking at the formula. So we are really in a position now where we know which two B sites to pick depending on the nature of the band gap that we want. So I'll end by showing you some cases where we have actually used this knowledge to teach the double perovskites to do what we want them to do. So I introduced the silver bismuth double perovskite, and I told you, it's the wrong color, it should be black. So the band gap is too large, and the band gap, if you remember, was indirect, so it was absorbing sunlight weakly. And using the principles that I outlined, we can show that if you add just a little bit of thallium 3+ into the bismuth 3+ site, so less than 1 atom% of thallium in the material, we can drive down this band gap to the exact band gap, well, close to the ideal band gap that we want for a single junction solar absorber. And just out of curiosity, we decided to go all the way to the all thallium material, and the band gap now goes down to the lowest value ever seen for a halide double perovskite. So moving from silver bismuth to silver thallium, 2 very good things happened. The large band gap went to a small band gap, and the direct gap moved to the indirect gap moved to a direct gap. And we can understand exactly why this happens. So when we replace bismuth with thallium, we do 2 things. One is we add thallium, and the other is we are removing bismuth, right? You don't need a PhD to say that. So it turns out that adding thallium changes the conduction band, and removing bismuth changes the valence band. So we try to show it in the schematic. It's a little busy, but if you will look at this red line here, this is my silver bismuth double perovskite. And as I start removing bismuth, I'm removing the maximum of the valence band at X, because I'm removing the s orbitals. And as my valence band maximum goes down, 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 the maximum is left at gamma. I'm not just removing bismuth, I'm also adding thallium. Thallium brings empty 6s orbitals, and that gives me a conduction band minimum that keeps going down, down, down as I add more and more thallium. And so I go from this large indirect band gap to the small direct band gap. So it's very satisfying to understand both alloying, so stoichiometric substitution, as well as full substitution. Now, this is great, except we don't actually want to work with thallium for any application that involves people, because I mentioned that thallium is 10 times more toxic than lead. But the beauty of developing very simple tools is that the knowledge you gain can be applied broadly to other compositions as well. So in this case, I told you that the empty 6s orbitals of thallium was the key player here to decrease the band gap and to go from an indirect band gap to a direct band gap. So we can then ask what other ions have empty 6s orbitals. And we don't have to look too far to come up with tin 4, which is isoelectronic with thallium 3. We know tin 4 goes into a double perovskite. And this just works like a charm, allowing tin 4 into the silver bismuth double perovskite basically mimics everything we saw with the thallium 3+, but now in a purely non-toxic composition. So with that, I didn't want to talk for too long because I wanted to leave plenty of time for discussions. So my congratulations to the impressive work done by the Faculty of Science at the University of Colombo. And also my congratulations to the new graduate students who are entering grad school next year. I don't have a summary slide. Suffice to say that it's a really exciting time to be a chemist. There's a lot that we can do, and there's a lot that we should do, particularly with respect to clean energy. So with that, I want to thank my phenomenal group of students who have conceived these ideas and worked very hard to bring us to where we are today. I'm grateful to these agencies for supporting my research program, and thank you for having me be a part of your centenary celebrations. Did I speak too long?
No, I think you're right on time. Thank you very much, Hema, for that interesting talk on double perovskites, their instabilities, and the methods developed by your research group to overcome them. And welcome everyone to the Q&A session. And you can send in your questions for Hema via the Q&A box, and I'll try to incorporate them as much as possible. Okay, so Hema, we have one question. The first question is from Professor Dhammika Disanayaka, and he would like to know, isn't it more accurate or easy to predict the band structure of if a band structure calculation program like Quantum Espresso is used?
Yes, so you can definitely get a more accurate band structure using any kind of DFT calculation. But we have been staring at these band structures for a very long time. And when we have theory collaborators that we work with all the time, and they give us a band structure. And when we ask, what information does this give us? It'll give us the band gap. It'll tell us about the dispersion of the bands, which tells you how fast the electrons and the holes will move. But it doesn't tell me what perovskite to make next. I don't know where my orbitals are. So then I can go back to my theorist collaborator and say, show me my s orbital. We are very difficult people, so we keep making demands of our theory collaborators. And then they can give you a projected density of states. They can answer every question we have. So all the information that we come up with is within the band structure, but it's not readily available for us. And what we do not get from the band structure as synthetic chemists is an insight into what material to make next. Which orbitals do I want in my B sites? It's very hard to generalize. It's hard to see trends with the band structure. But when we develop the band structure ourselves, I can tell you there's S character at X. So if I want to get rid of my maximum at X, I have to remove a little bit of S orbitals. So I need to remove a little bit of bismuth. That level of precision I have never got from a band structure. Not to say that it's not there, but it's not readily available. So we have found this method very useful just to give us an intuition for what our orbitals are doing. This will never replace a band structure. Nothing that I showed you is quantitative. We cannot give you a number. But for a synthetic chemist, I think it gives you much more intuition than just, a bunch of lines in a DFT calculation. But that's a very fair question. Yes.
Thank you very much, Hema. Another question. The solar cell efficiency of semiconductors depend on band gap of the material and has a maximum solar conversion efficiency is around 33% for a single PN junction photovoltaic cell. This was discovered in 1961. Is this limit valid as per the current findings, and can we make materials which have higher conversion?
Yeah, I think it's valid. I think the Shockley-Queisser limit is a valid limit. The way to overcome that is, of course, to use 2 absorbers instead of 1. So for a single absorber, there is a certain limit, which I think you mentioned at 30-something%. But then if you slap 2 absorbers together and make a tandem device, the limit goes up. So there's a lot of excitement in using perovskites for tandem solar cells. And the most compelling argument is that we are never going to beat silicon. The silicon industry is so advanced that we're not going to start from scratch again. But what if we took a silicon solar cell and put the perovskite on top and made a tandem? Now you can boost the efficiency. And researchers have made tremendous strides with perovskite on silicon tandems. And that's pretty exciting. I think these efficiencies are closing on 30. I haven't kept track, honestly, of the efficiencies, but they're very impressive.
Yes, actually, they have a very high efficiency. I was wondering, why do you actually have to put it on top of the silicon? Can you not do it the other way around, have the perovskite at the bottom and silicon at the top, so that the moisture contact of the perovskite will be less when you have a silicon layer at top? Is that not possible?
Right. So there are all kinds of architectures you can think of. The most simple one, the top absorber has to have a band gap of 1.8, and the bottom absorber has to have a band gap of, I forget, like 1.2. So silicon is the 1.2 band gap, and then you want the perovskite to be 1.8, and sunlight hits the perovskite first. So the high energy photons are absorbed by the perovskite, and then the low energy photons go through and then hits the silicon. And then the silicon absorbs the rest. And then you get the combined voltage. But that's just one, that's the most popular device architecture. There could, of course, be different architectures here.
Thank you very much for that. And so there's another question. how does the phase transition of perovskites affect the halide ion movement and the band gap?
Yeah, that's a great question. So the phase transitions will change the crystal structure. Once you change the crystal structure, you change the electronic structure, and then you change the band gap. And sometimes there are phase transitions to non-perovskite phases when you get a large band gap semiconductor using the same composition as your perovskite. So you basically have to operate within a regime where you have the crystal structure that you want and the band gap that you want. So it's certainly true that the perovskites have different phase transitions. I think a really good example of this is, I told you, methylammonium lead iodide is the most used material. Methylammonium is a big problem because methylammonium is in equilibrium with methylamine and HI. HI is a tiny little molecule, right? Hydroiodic acid. Methylamine is a small molecule. They're both gases. So even if you have a pinhole-sized hole in your encapsulation, the covering of your solar cell, you're going to start losing this gas. And then Le Chatelier's principle will push your equilibrium, and eventually your whole material will decompose and you'll be left with lead iodide. So we don't really want to use methylammonium. We want to use cesium. But cesium is not a perovskite at the temperature that we want to use it. So there's a lot of interest in stabilizing cesium lead iodide in the perovskite phase under operating conditions for a solar cell. This is a very active research area. Some might argue, you can't fight thermodynamics, and thermodynamically it's not stable, but there are some valiant efforts to stabilize cesium lead iodide. I think making nanostructures is one of them. If you make a nanoparticle, you can stabilize cesium lead iodide.
Thank you very much. I hope you got the answer. So another question. There are several questions, but let me try to put one more question in here. Is there a particular crystal orientation that will give you the maximum efficiency for these molecules when films are formed?
Is there a particular orientation? I'm not sure what orientation means. Certainly you want a film where the grains are continuous, and you want a high coverage continuous film. In 2D perovskites, the orientation matters a lot more. In 3D perovskites, it's you basically want a continuous, high quality, high coverage film. I hope I'm answering the question.
I think so. I hope so. Well, the last question, Hema, there are a few, but let me just put in this one. So the question is, the usage of rare earth ions facilitate the upconversion of NIR-IR wavelengths to UV visible wavelengths. Are rare earths good candidates for perovskites? Or upconversion is unnecessary for perovskites?
Yeah, that's a very interesting question. In fact, there's a very active research area within perovskites called quantum cutters. So basically, they use a doped perovskite as a top layer for your solar cell. And the material, so I suppose it's the opposite. It's not up conversion, it's down conversion. So it absorbs UV light and generates 2 photons of low energy light, which can then be absorbed by the perovskite layer. And the efficiency of this is very impressive. It's like almost 100% efficient. So this is kind of nice because, the UV light is often not used. So in this case, you can basically generate more photons for your perovskite device. But that was down conversion. Up conversion can in principle be used as well. I don't know of the efficiencies of up conversion and whether they will make a difference to the perovskite, because to my knowledge, those efficiencies are pretty low. But if you got a high enough efficiency of up conversion, yes, of course, you can then use, IR wavelength converted to visible light, and then you should be able to boost up your efficiency.
Okay, thank you very much. So since we are running out of time, we have to end the Q&A session at this point. Thank you again, Professor Hema Karunadasa, for taking off time from your busy schedule to educate us on teaching double perovskites to absorb sunlight. Now,
my pleasure. Thank you very much.
Thank you.